Welcome back, everybody. Hope everybody had a good holiday. Can you hear me? Testing, 1, 2, 3. Let's try that. Is that better? Hope everybody had a good holiday. Today we're going to actually start diving into some real material. So just to recall a bit about what we talked about last time before we close that out. We talked about history. I don't know, did anybody here find some of the history things interesting? Okay. You know, why study history? Well, it's interesting sometimes to figure out why we ended up with mechanisms the way we did. Anything in engineering pretty much has a historical component. Very rarely do you tear everything down and start over again. That's great when you have a chance to do that, but when you don't, then you're stuck with historical constructs, and it's usually good to understand where they came from. Not to mention there are some good stories there. We mentioned there were several distinct phases, kind of the beginning of time with computers where they took whole rooms and the computer was the thing everybody bowed down to. You know, the computer was expensive and humans were cheap. And then we kind of moved into this phase where the hardware got cheaper and cheaper until now. It's really about the humans, and we've got computers everywhere. You've got them in cell phones, you got them in iPads and iPods and cars, and, you know, yeah, we got a desktop or two, and yeah, there's a mainframe or two, but the little ones are kind of the big deal these days, and they're all there to make your lives, I might say easier, but perhaps more complicated might be a better way to put it, but that's okay. And as hardware got faster and more powerful, then we saw an evolution in OS techniques. We went from batch to multi-programming, which we're going to start talking about today, to time-sharing systems, and then we kind of moved into the interesting graphics and devices being everywhere, and you know, now we've kind of, you store your pictures in cyberspace, and you probably have no idea where that actually is, but you probably don't care until they crash and your pictures are gone, but we'll talk about that later in the term. And then, of course, this same progression happened at all the different scales. So you started with the mainframes, and they went through this evolution, and now we've got cell phones that are going through this multitasking evolution, and you've got commercials about, you know, Droid on the commercials. Is that pretty good? And it's really about moving those features from the big machines down into the little machines. And what's kind of funny is we keep finding ourselves in this situation where Microsoft has got 10 million lines or 20 million lines or 60 million lines of kernel code, and you wonder why it crashes, right? Okay. And then this was just showing you that the migration has been happening from the big machines down into the little ones. So today, what I want to do is we got cut off at the very end there talking about OS structures, so I want to spend a little time talking about finishing that discussion. And then we're going to start talking about how to provide multi-programming. Okay, and for the first half of this class or whatever, we're going to kind of assume that we only have one CPU. Okay, so I know I told you a lot about multi-core at the beginning of the class, but we're going to start by dealing with one CPU. We're going to talk about what processes are. We're going to talk about what threads are and address spaces. So these are terms that we'll have for the rest of the term. And we'll go from there. So to finish up a bit of our discussion that we didn't finish quite at the very end last time, this is a picture I've showed you a couple of times already in this class, which is the basic Unix system structure. And what you see here is it's pretty much a bi-level. There are two levels here. There's user mode and there's kernel mode. And kernel mode tends to be all of the things that we traditionally think of as the operating system. So file system, CPU scheduling, virtual memory. In the case of Microsoft, it's also graphics and a few other things are in kernel mode down here. And that is the protected mode. And the user mode is everything else. Those are your applications that are running using services from kernel mode. Okay, so this is what I would call the basic two-level flat structure that has been kind of around pretty much since the Multics days, okay, since the beginning of big kernels. And the question that I wanted to address briefly before we ended this, so this is a clear structure, right? You put all the stuff that's protected kind of together, and everything else is on top of it, and you hope that there are no bugs in here, because if they are, if a bug is in the file system, it could crash the virtual memory system because there's no protection boundaries anymore because everything's in kernel mode. Yeah, question.
Did you imply that in the Unix kernel that graphics was in user mode, not kernel mode? Is that correct?
You know, what I did was I didn't imply that because it depends on circumstances, but by and large, the graphics things tend to be more in user mode in Unix than they are in Windows, where they were pretty much moved into kernel mode a while back for performance reasons. So,
Why didn't Unix follow suit?
you know, maybe they weren't quite that crazy. I don't know. You know, it's not really, I mean, the graphics device isn't really something that you want to have necessarily protected in kernel mode and able to crash everything else. So it's not a particularly good protection scheme. This is an alternative to the two-level schedule. Okay, this is the notion of a microkernel, and I wanted to make sure we got this terminology out here. And by the way, I stole this figure from Wikipedia. Thank you, Wikipedia. But notice that this kind of on the left is really what I would call a monolithic standard kernel, and all of this stuff in blue is kind of the thing: virtual file system interfaces and file systems and interprocessor communication and scheduling and virtual memory and device drivers and da-da-da-da. All that stuff is running in kernel mode, and the applications sit on top of that, so this is all protected. In a microkernel, we've got a very thin microkernel, that's why it's called micro, that only does a few things. It basically schedules different tasks, it handles virtual memory, and it has a basic interprocessor communication mechanism. And then everything else is on top of that running in user mode in its own address space, so it's protected. So here we've got your applications. That's what we saw before. But you know, you might actually have device drivers running at user level. You might have the file server running at user level. You have other things all running at user level. Okay, and the way that in this traditional system, the communication is all via, you make a procedure call. Here, you can't make a procedure call because they're protected from each other, and so you actually have to use some sort of interprocessor communication mechanism for the file system to put files back to the application, or for a device driver to talk to the file system. Okay, so much of what we used to think of as the kernel and the big structure goes at the user level, and there's just a small core set of services. And the benefits of this are, one, it's very easy to extend a microkernel because you can easily add some new service without worrying about it crashing everything, because everything's protected from it. Okay? It can be easier to port an operating system to new architectures because you just got to start with just this microkernel piece. Maybe more reliable, there's better fold isolation, and so on. So these all sound like great things. What are a negative here? What negatives can you imagine? Yeah. Yeah, so one of the biggest problems with the original microkernel, which was Mach, was that it's very slow because this communication mechanism is slow. You're crossing protection boundaries for every communication between services. And I will tell you that when you get toward more modern microkernels, L4 is a good example, there are several other of them out there, they've highly optimized that communication. It's much faster. Okay, but the microkernel architecture hasn't really caught on all that much. In fact, it's come and gone several times over the course of time. So it's got all these benefits, which are fault isolation benefits, but then it's potentially got higher overhead. Okay? Now, what I wanted to toss up here briefly is, here is a modern multi-core chip. And you can imagine that you actually partition the chip up in pieces where you actually have things running in parallel, but they're using chunks of processors. So you might have something doing virus detection and being a firewall. You might have your GUIs and other video stuff going on here. You have device drivers and your apps. And they're all given parts of the chip. And you could imagine this being very much like a microkernel where the boundaries are not allowed to be crossed except by specialized code, except it's not as slow because these two things are running at the same time, and this message could be a very fast communication either through memory or even through a hardware messaging interface. So I just wanted to toss this up here because this is kind of the example of the way we think of the tessellation OS that we're doing in the PAR lab. It's kind of harkens back to microkernel in its organization, but has this advantage of multiple processors now, whereas before you had one processor that was being multiplexed. Okay? Any questions on that? Good. All right. So, unless there are any further questions on structure, microkernels, etc., then we're going to actually move on to threads and processes. Okay. So let's talk about concurrency. Now, the word concurrency, by the way, I should have put a definition up here, is a funny one. Does anybody know what's the difference between concurrency and parallelism? Yeah.
Parallelism, they are both operating at the same time, as opposed to concurrency, where they operate at intermittent times, where they could operate at the same time, but it's not specifically defined.
Yeah, that's good. So parallelism, you know things are running at the same time for sure. Concurrency is more, they could run at the same time, or they could be interleaved in any arbitrary way. Okay, and so we're going to be talking about concurrency, which, by the way, usually to think about concurrency, you have to make kind of that extreme assumption that they are running at the same time for correctness reasons to really understand them, even if they're not. Okay, so concurrency is going to be our topic here, but let's define some terms. So a thread of execution is going to be basically an independent fetch, decode, execute loop. Okay, and I will, how many people here have taken 61C? Okay, good. So you remember all your processor design stuff, right? So you had a program counter. We'll bring this all back to you. A thread of execution is kind of what you thought of as your processor in 61C, and it's operating in some address space. I'll make this clearer in a little bit. The term uniprogramming, one thread at a time. Okay, hopefully that doesn't surprise anybody. Things like MS-DOS, early Macintosh, batch processing. What's great about uniprocessing is it's easy for the operating system designer. Okay, they don't have to worry about one thing at a time. You get rid of concurrency problems by defining them away. Well, nothing can ever run in parallel, therefore there are no concurrency issues. Okay, isn't that great? That's get rid of problems by definition. Now, does this make sense for a personal computer? Okay? Certainly not today. I mean, you know, you're instant messaging and you're browsing the web and you're watching a video and you're listening to music and, oh yeah, maybe you're working on your homework. But yeah, many things at once is kind of the way we deal with things. And I find it kind of amusing, by the way, that all of these commercials that are out for smartphones, right? In the early days, a smartphone was something that you could read your email on at the same time, or not at the same time. You could read your email on and make phone calls and so on. And then there's been, have you seen these big ads? It's all about, well, you know, you could do one thing at a time, but on our smartphone, you can do multiple things at once, right? And they're making that as a feature. But you have to wonder whether the general audience quite catches that feature, right? It's interesting. So obviously multi-programming is the opposite, which is more than one thread at a time. And you know, this is Multics and Unix and Linux, OS 2, Windows NT, 2000 XP, Windows 7, Windows Vista, Mac OS X. Often called multitasking, but multitasking sometimes has other meanings, so we'll stick with multi-programming for a moment. But this is more the direction we want to understand in this lecture, and we're going to go under the assumption we have only one CPU. So if we only have one CPU, but we want to be doing multiple things at once, what do we got to do? Yeah, we got to multiplex somehow, right? Use more than one, have more than one thing sort of alternate in what they're doing on the CPU. Okay, and so that's kind of the tricky part of the OS. And many core, clearly multi-programming, right? That is almost a no-brainer. Okay, you got multiple processors, then obviously you got more than one thing going on at once. Okay, so any questions on the terminology? Now, what's the basic problem of concurrency? Is as follows. Your hardware is one of, right? You've got a single CPU for now, single DRAM, single I/O devices, right? the multi-programming API lets everything that's running think that they have exclusive use of the resources. Okay, so you got 4 programs running at the same time. Each of them thinks they've got the CPU. They think they've got the memory. They think they've got the I/O devices. And so the trick here is how to put this together in a way that avoids chaos while giving the illusion that things are running at the same time. And so somehow the OS has to coordinate all this stuff. So if there's multiple users or programs or tasks or whatever going on at once, multiple I/O interrupts, it's got to keep everything straight and somehow avoid chaos. I mean, the simplest thing to imagine here is you're sitting at a windowing system and your mouse is moving around. Every window might be doing something different. You want to make sure that when you click on the mouse, it goes to the right application. Right? Or when you start typing on the keyboard, it goes to the right application. Well, who does that? The windowing system, right? Somebody's got to keep that, and that may or may not be in the operating system, but this is kind of the point to be thinking about here. So the basic idea here is going to be using a virtual machine abstraction. We're going to decompose this difficult problem into some simpler ones and start by abstracting the notion of an executing program. Okay, and then we're going to worry about multiplexing the machines on top of that. And Dijkstra did this a long time ago with the system. Now that's, you got somebody who's got a lot of self-confidence if they call their system the system. Okay? Someday I want to be able to do that. Unfortunately, Dijkstra did it a long time ago, so it would be ambiguous, right? But what's kind of amusing is the multiplexing stuff that he did was a few thousand lines of code versus millions of lines in OS 360 with 1,000 bugs in it. And now today we've got 10 million lines. Okay, so what we're describing here has many layers of complexity that could go behind it. Now, okay, 61C, right? What's a processor? A processor is pink here on this slide, or whatever color that shows up on the screen. And what's inside of it is some registers. Okay, these are temporary storage locations. And some control circuitry that's going to do fetch and execute. So this could be a pipeline. It could be multi-out-of-order execution, multi-issue sort of thing. It could be arbitrarily complicated. But this is going to manipulate the registers and memory. Well, what memory are we talking about? Well, we're going to talk about our address space. And notice, for simplicity, it's just a 32-bit address space. But that means there are addresses that start at 0 and go up to 2 to the 32nd minus 1, which is 4 billion, some plus or minus a few, plus a few. And basically, memory is this place that can store values. Okay. Almost all of 61C has been covered. So what's the execution sequence here? Well, you fetch an instruction at the PC out of memory. You decode the instruction. You execute the instruction, possibly updating registers. You write results to registers or memory. You compute the next PC. You stir and repeat, okay, over and over again. And as a result, you've executed something. Okay, is that reminding everybody of 61C? Okay. How do we, so this is kind of an abstract execution model here. How do we multiplex multiple threads of control on a single CPU? What do we have to do?
Well, it depends, right? If you have hardware, you just have to finally frame multi-threaded, or you can have some sort of instructions to change the thread itself, or you can just have the instructions jump to a different address.
Okay, so you gave me several options, some hardware, some software. What are all of those options? What do they have in common? What are they doing? Okay, but what are they doing? Tell me about these registers or this PC and stuff. What's got to happen there? Yeah.
Each program or each process has a different values in their registers, so they have to be saved somewhere, and then they have to be switched back and forth.
Okay, so you gave me several options. In fact, we're going to show you a hardware one in a moment, just because that's a good discussion. But something in principle has to take the registers of the first thing, save them, load the registers of the second thing, start executing for a while, save them, load the registers of the third thing, start executing. Right? Everybody see that? We have to be alternating what's in the registers in order to give the illusion that we have many CPUs. Now, another way to look at that is as follows. Oops, PCs are basically executing instructions. La-da-dum. So here we have the illusion we want is 3 CPUs on top of a shared memory. And assume we have a single processor. What do? Well, we multiplex in time. So rather than every one of these things just running as it will, we do something more like this, where the virtual CPU 1 runs for a little while, then virtual CPU 2 runs for a little while, then 3, and so on. Okay? Now, I don't want to belabor this point if it's clear, but each virtual CPU needs some sort of structure to hold things like the program counter, the stack pointer, the registers, etc., the things that make that CPU, and again, we're talking in quotes there, unique. Okay? Are there any questions on this? Now, I see a few confused looks. Feel free to ask a question. I'm sure everybody has it. Now, let me keep going here. How do you switch from one CPU to the next? Well, to go from CPU 1 to CPU 2, you save the program counter and stack pointer and registers somewhere. You load the same things at the next one, next CPU, and then you execute for a while. Okay, and then you save all of its state, and you load the state for CPU 3, and you execute it for a while. Then you save CPU 3 state, and you load CPU 1 state, and continue for a while. Okay? Now, can anybody see any possible problems with this idea? Yeah?
Say in that graph, CPU1 modifies some like value, but stores that value as a register. But then you switch to CPU2, and then CPU2 again modifies that.
Mm-hmm.
But then you switch back to CPU1. Would CPU1 still think that thing that it modified is still?
Okay, so I'm going to say no, but that's a great question. Let's make sure we understand the question here. You're worried that CPU 1, which, by the way, all systems should at least have one CPU computing pi. You guys will learn this by the end of the term. It's very important. One of my favorite numbers. But suppose CPU 1's computing pi, which, again, is a very important computation. And what it's doing is it's got a register 5, which is part of the computation. It stores a value there. And now we switch to CPU 2, and CPU 2 modifies register 5. And then we go back to CPU 1, and it looks, and register 5 is wrong.
Well, you have different register windows in the hardware, right? So.
Okay, but right. So why is that not? So register windows in hardware. What about the software solution we just gave you? Why is what you just described there not an issue? Because at the point that we switched from CPU 1 to CPU 2, we stored out register 5 in CPU 1's state and loaded CPU register 5 from CPU 2, which executes for a while. And then when CPU 2 loads out, it stores out its register 5, CPU 1's register 5 gets loaded back. Okay?
I was actually thinking about something slightly different.
Okay?
Say CPU1 is reading a file with this, and it reads one file.
Right.
File and it stores it in the register.
Uh-huh.
And then, but then we switch to CPU2, and CPU2 modifies it.
Ah, okay. So let's pull files out of the picture here for a moment. You're talking about the memory here, let's say. Just okay. If CPU 1 does modify something and then CPU 2 changes it out from under it, and CPU 1 sees it something different when it comes back, we got a problem, right? That's a great thing to hold on to when we get into synchronization next week, and you'll see that yes, when we start talking about things that are shared between CPUs, then there's a whole bunch of interesting discussion we got to have. But as far as registers within the CPU themselves, those are non-shared things. And the only reason that we would have to worry about the shared state getting messed up is if the operating system's broken somehow. Okay? Good. Are there any other questions? We'll get to your hardware example in just a second. All right. So another question, or another problem, which you guys didn't notice, is what triggers a switch? Suppose CPU 1 is computing the last digit of pi and doesn't want to give up the processor to CPU 2. Then what? Well, it may not even be a fight, because if we don't design our operating system correctly, CPU 1 will just keep running forever. So there's got to be some way to make sure that these boundaries actually happen. Okay, and I put several of them. We'll talk about them over time, but one of them is actually a hardware timer goes off and forces us to switch. Okay, another one actually, which was very common in the early days of personal computers, is a voluntary yield, where CPU 1 yields every now and then. Okay, now the problem with that idea, as simple as it's going to be, and it's what we'll talk about next time extensively, if CPU 1 screws up and has a bug and doesn't call yield, then it's got the processor forever. Okay? And if you wonder why Windows 95 used to crash all the time, it's because it was possible to get stuck in these loops with never yielding. And the original Macintosh had this problem. And then other ways that the switch could happen is if CPU 1 goes to read from the disk and the data is not ready yet, then it will switch. Okay, so there's lots of ways of causing this switch to happen, and we're going to need to make sure that they happen frequently enough that we maintain the illusion that we have multiple things going on at once. Yeah?
Could you make the switch too infrequently when you, say you only have one process running? Do you get a performance cut if you are triggering switches too frequently? How do you handle that trade-off?
So when we get into scheduling, we'll talk a lot about the trade-off there. The bottom line is there's some overhead to unloading and reloading. And if you do that too often, then you end up with more overhead than computing. And I'll show you that in a slide. And so you got to make sure that that isn't really an issue. Now, it turns out if you only have one process and you yield, it's never even going to bother unloading. It's going to say, oh, there's nobody else to go in. I won't even bother unloading. And so you don't have that overhead. OK, good questions. Now, so what's property of this simple multi-programming technique I gave you? Well, all the CPUs share the same non-CPU resources, which was the source of that file or memory question earlier. They have all the same I/O devices, all the same memory space, etc. So far, we don't have a lot of protection in the system. Okay, the two different CPUs can screw each other up by messing up each other's memory. Okay, so consequences of sharing. Good consequences. Every thread can work on the data of every other thread. So it might be that you have some parallel search algorithm and you want multiple things working on at the same time. That could be good. Could be bad if one thread overwrites the instructions of another thread with a virus. Okay? And in some of the early operating systems, it's possible for user threads to overwrite the operating system. Actually, it's still possible if you've got a Microsoft system. Well, that's actually Linux, and all of them have that problem. So that's not a design feature. Usually that's a bug. So this unprotected model is common in embedded applications. Okay, so if you look at the operating system of a device running in your car, it probably is not assuming that there are multiple threads that could screw each other up. There's probably one thread running the brakes and one thread on a separate processor running the airbags. Okay? In fact, that's why you get up to 100 processors very easily. Windows 3.1 and the early Macintosh, that was like this as well. So all the things running, all the different apps, all shared memory together. And more interestingly, I don't know, have anybody ever played with an old Macintosh or a Windows 3.1 system at like a museum or something? No? So they're kind of interesting to play with because you get this illusion that multiple things are going on in different windows. But what actually happens underneath is every application cooperatively gives up the processor regularly enough that we make progress on all the different threads. Okay, so it's cooperative. And then there were some interesting things like Windows 95 in theory had protection whereby process A couldn't screw up process B, but there was still this back end for 16-bit compatibility where you could pop into this mode and completely overwrite the system. And so Windows 95 used to lock up all the time because it wasn't really protected. Okay. Questions? Now, let me, since the hardware technique keeps coming up, let me tell you about what if we don't want to have the operating system always do the switching for us. And it turns out that most processors you can buy these days do have something called simultaneous multithreading, or if you're a company like Intel and never want to use somebody else's term that pre-exists, you come up with your own, and so you call it hyperthreading. But what is that? It's a hardware technique for threading. And let me just show you the basic idea behind this, because it's kind of interesting. So the other thing which we won't talk about, because this is not 152, is that modern processors all execute more than one thing at a time, more than one instruction on a cycle. You'll hear a lot about that if you take 152. But what that's showing you here is time is going down, and each slot represents a cycle, and each column represents a functional unit. So there are 3 functional units, and in this case, this cycle here, functional unit 1 and 3 are busy because they're color-coded in a dark yellow. Functional unit 2 is not busy. Okay, now you guys can parse this, right? And so in this cycle, nobody's busy. Here we've got a couple things busy and so on. And why are the gaps there? Well, they're there because of dependencies and all sorts of interesting stuff you hear about in 152. But notice that in this situation, we're not using up all the cycles we could. Okay, not all the slots are full. And so if you have a multiprocessor, you might put 2 of these together, and each of them has idle slots. In a hyper-threaded or simultaneous multi-threaded system, what happens here is you put 2 threads together into the same pipeline, and they share the slots, and as a result, you end up filling up more of the empty slots. Okay, so that's a basic simultaneous multi-threaded processor. Now, to make this work, of course, this means that the hardware itself has got 2 sets of registers and 2 program counters and 2 branch predictors and 2 of a few other things that we won't go into too much. But the bottom line is you can load 2 threads into the processor at the same time, and the processor on a cycle-by-cycle basis is interleaving instructions. Yes?
Does this assume or require shared memory, like the 2 applications do the same memory space?
So it does not, actually. So these hyper-threaded threads actually have their own address space and are protected from each other. You can set it up so they have shared pages, and I'll mention that at the end of the lecture, and then they'll share things, but they don't have to. Now, basically, the hardware can schedule each thread as if it were independently running on the CPU, but you can imagine that each thread runs ever so slightly slower than it did by itself. Okay, hopefully that's not a surprise to anybody. It's just kind of the game. So the original technique was actually called simultaneous multithreading, and there's some fairly good papers up from the University of Washington where this was originally originated, and then pretty much everybody who was building big out-of-order processors adapted it. Intel's the only one that called it hyperthreading, from what I know. But if you're making a large fraction of the world's chips, you can rename things any way you want. Question? Yeah.
Does an operating system, does it or can it differentiate between a hyper-threaded architecture and a multi-core architecture?
Yes, there are bits that you can look at, but for most intents and purposes, the threads look like separate CPUs, and at the operating system level, you can tell them apart. But oftentimes, the operating system doesn't even bother trying to tell them apart. This is why, by the way, if you have a hyper-threaded system, you go to the task manager or whatever, and you look, and it shows you have multiple CPUs, even though you think you only have 1 core. Or you think you have 2 cores, it shows you 4. Well, that's because of the hyper-threads. Okay. So any other questions on that? We'll go to some administrivia. Good. So wait list is pretty much down to the end game. We actually cleared a couple of students this morning. I know I told you I'd shut it off last night, but as of right now, we took out pretty much grad students. I apologize. You guys are welcome to sit in. There was one kind of undeclared major who's way at the bottom of the list. And so at the moment, we have 7 juniors left on the list. Now let me tell you about the section sign-up, which did anybody not do section sign up last night? Okay, did anybody do section sign up before Monday? There was a couple of you. Did you redo it as was posted? No? Okay, so you may be missing. So as of right now, we've only got 147 total students in groups. You should all take a look at the online tentative group assignments. Good thing is we've got nicely balanced sections. So our TAs are all breathing a sigh of relief. The bad thing is we're missing students. So if I have 147 students in there, that means I'm missing 6 to 8 students somewhere. It may be because we cleared everything out about noon or 1 on Monday, and then I sent mail saying make sure to... Did everybody get that mail? Or said please did anybody get that mail from me saying please register? Some of you? How many people got a message from me about that? I'm just curious. Because I sent mail using the BSpace things, but I guess that doesn't work. Has anybody gotten, did you get the mail from me originally about sections being canceled the first week? No. Did anybody get that?
There's no tab for 162 on BSpace that I can find.
Well, there isn't because I don't make it public, because it's not for you guys, but it has all your email addresses and it's supposed to be sending mail to everybody, but I guess that's broken. Yes?
Yeah, this actually happened to Dan Klein last year. If you send out like a huge mass mail, sometimes Gmail will filter spam.
Okay, well, we'll have to find a better way to... so make sure that you run register on your accounts and get emails in there, because maybe I'll go through the department to do this instead. If you're not in a group, we'll assume that you don't exist. Okay, I realize this is, you know, on the existential scale, this unfortunately seems a little bit balanced in a funny direction, but you have to be in a group. We also have one 3-person group that's listed on that site, and I understood that we have another one that lost a member or two. Is there anybody who doesn't have a group? Oh, all right. So if you're in a 3-person group, you need to come talk to me. We need to figure that out, because we shouldn't have any 3-people groups. We may want to make sure if there's 5-person groups in the sections that have a 3-person group, maybe we could get somebody to move over or something. Okay. Are there any questions on group sign up? Please look. Tentative assignments are up, and I only have, like I said, 147 students, so something's wrong there. Okay. Reader is ready in a couple of days, I think. Yes?
I called a copy central on Thursday England and said he had no order for one.
When did you call him?
Today. Like now.
Oh, really? So we had apparently, so you have no order for 162?
I already ordered yesterday.
Ordered it yesterday evening. Maybe he was confused.
Because he said a bunch of students have been calling and they don't even have any order for 162 at all.
I guess we'll check on that, because we'll check, because it was actually put in yesterday, so hopefully it'll... Anyway, the point is it should be there by Friday, so... and I will put an announcement on the website. So... but anyway, yeah, it's done. It's just it doesn't exist quite yet. No. As you might have figured out, I don't really use BSpace for anything. So I don't know. I guess maybe there's some major advantage to using BSpace, but how many people think there's a major advantage to using BSpace? I won't quote the statistics on the webcast here. So Tuesday, woohoo! You're going to start projects. So what that means is you got to get going. Oh, and I forgot to put in a link. Friday, that's 2 days from now, you should attend your new section. Okay, do not go to your Telebears section. That is now toast. Doesn't exist anymore. You should go to your new section. Okay, because then that will be the section you will attend from this time on. All right? Any other administrivia questions? Other than missing 6 or 8 students, this has been one of the the least problematic sign-ups times I've ever had, because sometimes we end up with one section that's got like 3 people in it, and we have to end up moving it around. So I think we're good. Okay, no other questions. So by the way, the wait list will be absolutely emptied by Friday. So I don't know what's going to happen. I'm thinking those 147 students may indicate there's a couple of students that dropped and didn't do so. If you know of a friend that dropped and didn't indicate to that formally, they should do that sooner rather than later. Okay? Okay. So, how do we protect threads from one another? Well, we need a few things. Okay, so first of all, we need to protect memory. Okay, remember the very first day I told you about protecting memory. All right, and you want to make sure that every thread doesn't have access to every other thread's memory space unless that's an intended thing. Okay. The other is we got to protect the I/O devices. Basically, every task does not have access to every device, or at least it doesn't have access to it in its raw form. Because if it did, then we have no file system protection, we have no networking protection, there's all sorts of problems. Okay? And we need to protect access to the processor. Now that seems a little funny given that the thread's running on the processor. But what I mean is, we got to make sure that a thread can't permanently take the CPU and refuse to give it back. Okay, so that means, for instance, we use a timer to cause the thread switches. Okay, and it must not be possible to disable the timer. You can see the obvious ways we can go with this. Okay, is that clear to everybody? So let's recall the program's address space. So here is a little bit more data or more information than we normally talk about. But here's a 0 up to whatever the max address is. And oftentimes we have the text area, which is where the instructions are. And then we have data, which is static data that's allocated at the beginning of the program. And then we have an area called the heap and the stack. Okay, so what's the heap? Dynamically allocated memory. So you probably remember malloc from 61C, right? Or in something like Java or C++, it's probably, you remember the new designator, right? All of that stuff is in a range of memory that typically grows some direction, let's say up. And then the stack is, what's the stack? Okay, well, the stack is pointed at by the stack pointer. I'll buy that. Go ahead. What? So it's with local variables. Okay, so that's basically when you make a procedure call. You remember the most important program you guys ever learned in 61A was how to do Fibonacci recursively, right? You will remember that till the day you die. Okay, I can't say that that's a good thing you'll remember it, but you remember the whole recursive aspect to that where you call the same thing over and over again? So a procedure calls itself. Okay, where do those different copies of the variables go? They go on the stack. I'll talk about this a little later. Why do we have to grow the stack? Well, because you could have very deep recursion, in which case you need more stack, or you could have shallow recursion, in which case you need less stack. Okay, now what's the blue space here represent? That represents unallocated memory. And when we get to the level of sophistication of talking about virtual memory, this actually represents part of the address space that may not even have any DRAM backing it yet. Okay, it may just be a hole. Okay, this is one of these things where you write the bits here and they show up in another galaxy somewhere. So what's the address space? The address space is a set of all accessible addresses, which is this, and the state associated with them. So places that are real and not holes actually have some data. And so when you read and write it, you'd like to get the data to return that you wrote recently. But maybe in this hole, when you read and write it, nothing obvious happens because there's no state associated with it. Okay, so those are kind of two different types of things. And in fact, when you read or write a value, what might happen? Nothing might happen. Okay, if you're in the middle of an empty space, it's possible that you could write there and nothing would happen. Now, it's probably more likely that if you write in this space, what happens? Say again? Well, No. So what might, if it were just like regular memory, it'd be one of these guys. But here we actually have a hole. So what happens, do you think, when you write a hole? Yeah, so you get something often called a segmentation fault or some sort of exception, and that's because this is not real memory. So notice the difference, that's segmentation fault. So the difference between writing in a spot that's allocated and writing in a spot that isn't allocated is actually the processor complains. Okay? And then there's other things that could happen. You could have a section that's called read-only, like the text segment is often read-only, and if you write there, perhaps your writes just go away. Or perhaps they cause another seg fault, which is a read-only seg fault. Okay? Now we will talk a lot about how to implement this stuff when we get into virtual memory a little later in the term. So here was the trick of protecting the address space, right? So the set of all addresses here and here are mapped to a different set of all addresses. And as a result, nothing in this address space overlaps anything in this address space. Yes? So malloc is a funny thing. So if there are pages attached to it, malloc just allocates out a user space. On the other hand, if malloc has nothing to allocate, then it actually does something, a system call called sbreak, which asks the operating system to fill in the hole with some more pages, and then it goes back to doing its thing in user mode. That was probably more information than you needed, but why not? So here we are. The two address spaces that are virtual actually end up mapping to the physical address space. And you might ask the question, well, if this is 2 to the 32nd things, and this is 2 to the 32nd things, and DRAM is probably, well, today it could be 2 to the 32nd things, but it's less, then how does this all work? How do you avoid having overlap? Yes, question. Oh. The microphone isn't working? Oh. Testing, testing. Yeah, I would say that's bad for the webcast. Hold on one moment. When did it die? 10 seconds ago? Okay. All right. Let's take a 3 or 4. Let's take our 4-minute break and come back. I'll get some batteries. We got them over here. 4 minutes. Okay. That's all right. Go ahead. We're still breaking. I just want to make sure that people in webcast land know that we've got a mic working. So we're still breaking right now. For you guys can have another couple of minutes. We seem to have an actual working mic again. So that's good that we noticed that before it was too late. So I understand it went out at the beginning of this slide, but the point of this slide was to remind us what we have talked about before, which is the virtual address spaces, which are in green, and the physical address space, which is in blue. And we have a mapping from the virtual to physical. And the fact that these all might be 32-bit address spaces isn't a problem, because we probably have a bunch of holes in the green ones, as I just showed you, right? From back here, there's probably a hole in there, at least one. Okay? But because of this address translation mechanism, we can actually protect threads running in this address space from threads running in that address space. Okay? Except what? What do we need to do to make that work? Yeah. So first of all, we need to hand out this memory in a way that doesn't overlap. Okay, what else? What about these translations? Think about when we're multiplexing. Yeah. Don't make them user writable. Yeah, that would be bad. What else? Think about when we're multiplexing CPUs. What do we need to do with the translations? Yeah.
Store them somewhere else.
Yeah, and?
Reload them back.
Yeah. So somehow we have to make sure that when we go from switching from CPU 1 to 2 to 3 to 4, that we swap in CPU 2's map and CPU 3's map and CPU 4's map. Okay, now it turns out that's going to be really easy when you start learning how this works, because the map is as simple as putting in a new base pointer into a register. So that's actually going to be easy, but you don't have to worry about that yet. So we're about ready to talk about what a process is now. We've sort of been throwing up the word thread, but what is a process? And we're going to start with the traditional old school Unix version. And it's basically an operating system abstraction to represent what's needed to run a single program. You'll find that right in your book. And what I'm going to describe right now is often called a heavyweight process. And the reason for that is what you'll see in a moment. But formally, it's a single sequential stream of execution in its own address space. So it's a single thread running in its own address space gives us a process. Okay? It's got two parts. One is the execution piece, which is the thread. It's code executed as a single sequential stream of instructions. And it's got the state of the CPU registers. It's got program counter. It's got stack pointer, etc. And it's also got some protected resources associated with it, like main memory state, the contents of the address space, I/O state, file descriptors, etc. Now what's interesting is, as you imagine, when we switch from one process to the next, we're certainly switching out the program counters and the registers of each thread, but we're somehow switching the resources as well. And I sort of suggested on this previous slide here that to switch, for instance, memory resources, it's as simple as changing the translation map. Okay, but that's part of this multi-processing that we're talking about here, okay, multi-programming. Now notice that a heavyweight process has no concurrency, which means there's only one thread, okay, inside this. So this is very traditional Unix processes. Everything that's independently running has its own address space and a single thread in it. If you want to have two things running at the same time, you actually construct two processes. Okay, very heavyweight. Now, how do we multiplex these processes? Well, current state of a process is held in a process control block. These are all words that you'll start reading in nachos soon. But what's a process control block? Well, it's got some header state, like what its state, I'll show you in a second, like what its number is, what the program counter is, some registers, what memory does it have, what open files does it have, etc. Those are all in the process control block. And in this not quite multi-core world yet, we only have one process can be running at a time. Okay, we're still in that mode because we only have one CPU. And we give out CPUs to different processes. That's a scheduling piece of what we need to do. Okay, now it turns out that scheduling is interestingly complicated enough that we'll spend several lectures on it in a week or two. but the idea is deciding which process gets the CPU and resources when is called scheduling. Deciding how to make sure that resources assigned to one process don't get used by another process, that's protection. Okay, and that's a different part of this whole process abstraction, and it's about controlling access to non-CPU resources. So example of memory mapping, that's the actual translation, is the way we do protection for memory. Basically, I/O we protect with the kernel user address or kernel user duality, which basically says that in order for the user to use an I/O resource, they have to go into the kernel, and the kernel makes sure not to let one user use somebody else's resources. Okay, so we can always do that, right? I showed you at the beginning of this lecture, I showed you Unix. It's got this huge amount of stuff in the kernel. The thought there is that the kernel code is perfect and always works, and therefore it will not hand resources to people that aren't supposed to get them. Okay? All right. So let's look at this overhead of scheduling here for a moment. So here we have process P0 is on here and P1 is on here, and since we only have one CPU, if you kind of look at the time that P0 is successfully executing instructions, and P0 is successfully executing instructions, and P1 is successfully executing instructions, those don't overlap. Okay, hopefully that doesn't surprise anybody, right? Does that surprise anybody? Right? They don't overlap because only one CPU, right? Now, what I'm trying to show you here, though, is process 0 is running for a while, and then the operating system gets invoked to switch to process 1. Well, what does the operating system do? Well, a whole bunch of stuff. It saves state into the process control blocks. For process 0, it reloads state process control block from process 1, and then it starts running process 1. And then later we switch back into the operating system to do the thing in reverse, and now we're back to 0. And if you notice, there's overhead there, okay? Because while you're in the operating system, no process is making useful progress. Okay, so that operating system in this case is pure overhead. And so there was a question earlier, which was a very good one. What happens if you switch too frequently? Well, you spend all of your time in the operating system wasting your time switching, and you never actually execute anything. Okay, so there's going to be a trade-off when we talk about scheduling between fine-grained division of a CPU, which could be a way to give the illusion that things are really running at the same time, and avoiding too much overhead. So we're going to have to adjust that, what we're going to call the quanta, which is how frequently we switch. Okay, and so this is called a context switch. There's a term that you should now be comfortable with, which is we're switching context from process 0 to process 1. Okay. Now, go ahead. Context switches are pretty quick. Though, you mean how frequently do they happen, or? So how long it takes might be 2,000 or 3,000 instructions. Okay, and that's a fast one. You know, it can be more than that. It can take you half a millisecond or something to do that. But typical context switch times are in the 10 millisecond and 100 millisecond range. By the way, the more modern the operating system is, the longer the context switch overhead is, because there's more stuff that they do. So that's why the simplistic operating systems are the ones that have low overhead. It's kind of a. The other thing I wanted to mention here is if you've got hyperthreads, then you could actually have two processes loaded at the same time, and that overhead switching in the hardware, and there's no overhead there pretty much. Okay, because the hardware is doing it for you. All right.
Even the super scale, but I mean, even with the 200, 500 instructions, you also have super scale, so you can do multiple increases in memory and produce it as well.
Yeah, so.
Your IPC, if it's less than, or your CPI is less than 1, then you're, or greater than, or less than 1, then you're actually doing better for it. If you have multiple instructions. So
Yeah, it's hard to. It's 6.5 of 1.
can't exactly just say instructions is for multiple times.
Right. All right. Yeah. That's can get very hard to analyze exactly, but okay. Any other questions? Now, what's the process state go through? We'll talk about this next time in more detail, but And this is just an example, but you can imagine you create a new process. It has never actually run yet. When it's got all its resources, then it gets put on a ready queue. And then what will happen is the scheduler will pull things off the ready queue, let one run, and eventually there's an interrupt. We'll go potentially go back to the ready queue. And so this loop here is kind of the main multiplexing loop where we go from things that are ready to run and things that are actually running. And if we have one CPU, there's only one thing over here. If we have multiple CPUs, then there might be multiple of them here. And then every now and then, a running thing actually tries to do some I/O. And so it may actually take a transition down to a waiting state. And this could be waiting on a queue for a network or the disk or whatever. And when we take that transition, again, something will be pulled off the ready queue to run. So basically, new is not run yet or even put in the ready queue. Ready is ready to run but not running. Running is running. Waiting is waiting. You guys get the general scheme of this. And terminated is potentially dead, no longer runnable, but not yet given back to the system. So-called zombie processes. Has anybody run into those before? So those are things where you do a PS in Unix and you see these things and sometimes they got a little Z next to them or whatever. Those are processes that are dead but not freed yet and they're in a funny state. Okay? Question, yeah?
Do schedulers generally bill a process that is in the waiting state?
So do schedulers bill a process that's in the waiting state? It depends on what the scheduler is doing. So basically, scheduling is a very general term. Again, the scheduler is going to have a couple of different possibilities. They'll have usually actual runtime, which doesn't get billed when it's waiting, and then there's sort of real time, which is not really billed against the process. So I think in general, it's kind of what you're thinking, which is when it's waiting, it's not really billed for it. But if it were using resources of some sort, then it might be billed for it. And so specialized schedulers might do that. But in general, it doesn't. OK, so I think I showed you these guys. OK. Questions on process state? And of course, this is, different operating systems have lots of different states. These are just kind of indicative of what's going on. In fact, there's probably many types of waiting state depending on whether you're waiting on certain types of devices or not. Yeah?
When a process is being saved, like in the slide 20, is there a special state that the save process is in?
When it's being?
When it's saved. Right before it's saved, is the state of the process changed?
Oh, you mean when we're going from running to ready?
Yeah, like...
Yeah, well, it's... all of these transitions are done atomically inside the kernel. So, if you're worried about does it change state before things are saved out or not, that's kind of invisible, hopefully, to anything that could notice. OK. All right. Other questions? So, here's a different view of what I just showed you here. This is the queue level view. So here are the states of a given process. This is kind of showing you what queues might be in the system, and this is right out of your book. And basically, the process control blocks move from queue to queue. So things that are ready to run are sitting in the ready queue. The scheduler pulls things off the ready queue and puts them on the CPU. Then how do they exit the CPU? Well, one thing they might do is they might actually make an I/O request, which is a way to exit the CPU. Or they might run out of time. So this, when I say time slice expired, this is saying that we give a CPU up to 10 or 100 milliseconds, right? And if that expires, then they take this path back to the ready queue. Or the CPU might actually produce other processes, okay? In which case, we go through the forking process, and now we have two things in the ready queue. Or the CPU might execute wait, where it wants to wait for an interrupt or wait for a network message or whatever. Okay, so if you were to actually look at the operating system from a queue standpoint, there are lots of queues that a process control block can sit on. And there's only, in this instance, one CPU. So process control blocks that are in queues are not executing. Okay, I mean, I think that sounds maybe simplistic, but I thought I would say it anyway. Okay? And what's kind of nice about the queue-based view of this is if you've got a process control block that's waiting for data to come back from the disk, you put it on a queue associated with the disk, When the data comes back, then you can take it off that queue and put it back in the ready queue. So these queues make it very easy for the things you're waiting for to wake you up when they arrive. Yeah?
Does that mean that within a single heavyweight process, you can't have two lightweight threads, one waiting on I/O and the other using CPU?
That's right. So far, we haven't put more than one thread in a process. This is heavyweight. This is old school. We'll get new school in 3 slides. Yes?
In the monolithic kernel architecture you've been discussing, does the kernel have more than one thread of execution?
Say that again. In the monolithic kernel, does the kernel have...
We've been discussing the monolithic kernel, right? Is there room for the kernel to have more than one thread of execution, or does that automatically imply that there's only a single thread of execution?
No. So monolithic and multi-threaded inside the kernel aren't necessarily the same thing. Really old school kernels, there could only be one thing only one thread actually executing in the kernel at once. Everybody else was either asleep or out of the kernel. And now today we've got multi-threaded kernels, which is obviously all the rage because of multi-core, and that's actually causing people problems because then you got synchronization issues and so on. Okay, good question. Any other questions? Good. Now, what does it take to make a process? Well, you got to make a PCB. Okay, that's probably expensive. That's a kernel malloc operation. You got to set up new page tables. That can be much more expensive depending on what you're doing. Okay, and we'll talk about what the format of a page table is later in the term. Here's an interesting thing, which I'm just going to mention once to you, but the semantics of fork in original Unix were that the child process got a complete copy of all of the data of the parent. Okay, I don't know, this is some genetic transfer view of life or something. But what was interesting about this is if the process had a gigabyte of data and you make a new child process, you'd first copy that gigabyte into completely different memory and then execute the child process. Okay, so that sounds expensive. And you can see why people didn't want to create too many processes because they're expensive just to create. Now, fortunately, they sort of very rapidly came up with ways of fixing that, and there'll be something we call copy on write, where the child essentially has a copy of the parent's data, but only because it's got page tables pointing at it, and it's only if one of them writes that you get new copies. And so you can make these copies that only happen when changes happen. We'll talk about that when we get into page tables later. What's even better is Linux has a special type of fork that doesn't even require this copy. So many people realize that ultimately these semantics were kind of silly. So, and of course, another thing that typically has to happen to create a new child process is you got to copy all the I/O state. So when you create a child process, oftentimes it's got copies of standard in and standard out. It's got copies of the files that were open and so on. Okay, and so that stuff's got to get copied. Okay. Now, is a process the same as a program? Okay, here's your philosophy for the day. Is a process the same as a program? Okay, and like all good philosophy, depends on the answer you want to give, right? So A, a process is more than a program. Why is that? Because the program's just part of the process state, right? Here's the program, but there's also memory state like the heap and the stack and stuff. And so it's only when you start executing the program, it gains all this state and it becomes so much more than it was just as a process or as a program. Okay? Now, of course, a process is less than a program. Okay, this is the philosophy part. And why is that? Well, because the program might involve creating a whole bunch of processes. So a great example of that is every time you type compile, like by using CC or GCC or whatever, oftentimes it starts up a pipeline of processes. There's a C preprocessor, and then there's a compiler, and then there's an assembler, and then there's a linker, and there's a loader. And these things are all different processes that are piping data between each other. Okay, and so there's many processes to the program that you're using for compiling. Okay. So I think the best you can get out of this is a process is more and less than a program. How about not the same as? Okay. Now, let's talk about a couple of other things here before we sort of finish out the hour. I think first thing we want to talk about is if you make something a program that has multiple processes in it, then those processes have to talk to each other to really collaborate on whatever you're doing. All right, and this is kind of the beginnings of parallelism. When we get into synchronization, we're going to deal with this problem a lot in a couple of weeks or a week and a half. But conceptually, here's three processes. They want to collaborate together or cooperate. They got to talk to each other somehow. Okay? How do they do that? Well, first of all, one problem we've just discovered or just discussed is that this is kind of a high creation and memory overhead just to make these things. So we want to make sure that when we create them, we don't throw them out too frequently because these are heavyweight processes. Context switch overhead's pretty high, so maybe in that instance we don't want to be communicating too frequently between these, causing lots of context switches, or it could be expensive. But bottom line is we need some communication mechanism, or there's really no point to making multiple of these things to try to do the work together. So what are some options? Well, one of them that gets in the way, the thing that gets in the way is we've got separate address spaces. Every one of these has its own address space, so it's not like you can write in the memory of one process and read it in the memory of the other. Right? Remember, we spent all this time making sure that the memory spaces didn't overlap. So, what do we need to do? We need to selectively punch holes in that protection in order for them to cooperate. So one of them is we can come up with shared memory. Gee, just like we can make sure that none of the mappings overlap, what if we made sure that one of them overlaps? Now suddenly there's a selective hole, keyhole, right, through which two processes can talk to each other. Okay, and another one is message passing. All right, I talked about interprocessor communication when we looked at microkernels earlier. This is a case where you actually send a message. So the simplest example everybody here is familiar with is you set up a network connection and there's two sockets on either end and these are on separate machines and they're communicating over the net. Okay, that's something that probably you guys sort of dream about in your sleep, right? Because it just happens with every device you own. What about on a single box? You can actually set up a socket connection between two processes and they can send messages to each other. Okay, so again, this is another selective hole in our protection. Yeah, question? How fast is message passing? Well, it varies all over the place. Okay, now remember what I said was microkernels in the original form went away very rapidly because they were too slow? Part of the reason for that was the message passing was too slow. And people spent years worth of research to how to make that faster. The other extreme from what I just mentioned there is you can have hardware support for messaging, in which case you send messages from one processor and they show up in the other. So basically it varies all over the place, unfortunately. Yeah, question?
Does the other process always have to be waiting for a message, or is the hardware performance or something with internet so you have a message?
So here I have so this is a great question which you guys are going to answer for me. So the question was, for those in web space, if these two, process 1 sending a message to process 2, does process 2 have to be waiting for the message? That was the question, right? More or less, yeah.
As long as you have an intermediary handling the actual messaging, there's no reason there couldn't be a queue.
Okay, queue. The operative word here is queue, yes. So all of these message passing technologies that you might use, there's a queue involved. So this doesn't have to actually be scheduled, which is a really great thing if we only have one processor because, well, this guy's sending, this one is certainly not running. Right? So basically, I think the right answer to your question, if I got it correctly, is there are queues in all of these message passing primitives. Did I catch it, or was there a different question?
It was more like, I'll ask you later. It's kind of a little different.
How does process 2 know that it had a message come in?
Kind of, yeah.
So, the problem with polling, so that one idea is process 2 could sit here and keep looking, do I have a message, do I have a message, do I have a message? The problem with that is that wastes CPU time, and when you're on one processor, that's a big waste, because when you're polling here, you're not sending over here. And in fact, we'll actually dock you for solutions that do what we call busy waiting later in the term. You'll see what that means. A better solution is actually you can use, there are facilities like Select and a few others in the Unix kernel that say, put me to sleep until something arrives. And as soon as it arrives, then process 2 gets put on the ready queue. That answer your question? Good. OK. Now, let me just show you the shared memory idea. Very simple. Remember how earlier we made sure that none of our translations overlapped? Well, now we make sure that one of the translations overlap. And now this little pink page is something that program 1 or process 1 can write into here, and process 2 can read from here, and the data transfers from one to the other because they're sharing the same physical page. OK? Everybody got that? OK. What's cool about this is extremely low overhead because it's as cheap as writing and reading memory. OK. So I guess we've been talking about IPC, so I won't go into this too much. But think of this as a local abstraction very similar to the network. So you set up a connection, you send stuff, you receive stuff. OK, we'll talk more about messaging later in the term. So before we close out, let's talk about modern lightweight processes. So a modern process has more than one thread. OK, that's a big surprise. It took a decade for people to realize that was a good idea, I guess. But the idea here is the process still has one address space, but it has multiple threads in it. And so often the term multi-threading will come up, and this is a single program made up of a number of different concurrent activities. So why do we separate threads from processes? Well, in the old days, you'd only talk about processes. The reason we separate them today is the thread is the concurrent piece that's executing an instruction stream that we can have multiple of them inside a process. So the process is the container that has threads that are executing and various resources like memory and address spaces. Okay? And so you could say that a heavyweight process is a process with one thread. Question? Yeah. Yeah, so threads in the same process all share the same memory. Okay, by definition, and therefore they can easily cooperate. Okay, that's like that example I showed you with shared memory earlier where we had to work to give overlapping address spaces. Here it just happens. The idea is that inside a process with multiple threads, every thread's got the same memory space. Okay. So here's an example of single and multi-threaded processes. See this? So here's a monolithic thing. It's got one thread. Here's a multi-threaded process. It's got 3 threads. Okay. Did you guys all catch that? Should I explain that again? So single-threaded's got 1 thread. Multi-threaded's got multiple threads. What's kind of interesting here that you may not have caught is the multi-threaded process has multiple copies of registers and multiple stacks. Why is that? Well, every thread is going to need its own stack. We're going to talk more about this next time. Okay? So the thread is the active component, and the address spaces are the passive component. And why have multiple threads per address space? Well, because in this scenario, we can easily have these guys collaborate together. And it's not a big deal because they just share everything. They also can crash each other. But the point is that this boundary, the process boundary, represents something from the same person, coder, entity, whatever. And if it crashes itself, then it's broken. But it's not screwing somebody else up. Okay? So the fact that these threads can screw each other up is kind of a byproduct of the fact that they can share so easily. I just gave you the positives and the negatives of that. Okay. So examples of multi-threaded programs. Well, embedded systems often have a multi-threaded component to them. More than one thread in the same thing. Most modern OS kernels are multi-threaded. This question came up earlier. Unfortunately, once you have more than one thread inside running at kernel space, now each of those threads can screw each other up. Remember, I just said that. And there's much more that can happen inside the Linux or Unix kernel to screw each other up. Okay, so that's a problem. Database servers, a lot of other things. Okay, let's see. I had a few other examples. Network server. We're going to talk about thread pools a little bit later in the term. And the point of that is that multiple threads can be handling requests from different people in the world, thousands of people, all collaborating on the same data in the web server. Okay, that'll be a good example. Okay. So the thread state, just to close this out, state shared by all threads in a process are the memory contents, the I/O state. That's common. What's separate? The private part for a thread is the thread control block, TCB. Okay, what has it got? Well, this shouldn't surprise you because we started with this, right? It's got the CPU registers, it's got the stack, etc. Okay. And the stack, I just wanted to give you a picture. I'll show you this next time. Here's a stack. All right, you should remember this from 61C. Here's a piece of code. A calls B and B calls C. Well, A gets temp equal to something. Here we have A with temp equal to 1. It calls B. B calls C, and so on. And this stack gets formed, which is the basically tracking the call path through here. Okay, we'll talk more about that. But this kind of shows you why every thread needs its own stack. Okay, because every thread's doing something separately. All right, I think we're going to finish up. So we can classify real address spaces. This is our last slide. In between one and many address spaces, one and many threads per address space. So early MS-DOS and the Macintosh had one address space and one thread per address space. Basically, a lot of embedded systems kind of have one total address space but many threads. Traditional Unix had kind of one thread per address space but many address spaces. That's lots of processes. And kind of here's where we are today with many address spaces and many threads per address space. Okay, I think that was all I really wanted to talk about. So in conclusion, processes have two parts. They have the threads, which is the concurrency part. They have the address spaces, which are the protection part. Concurrency is basically by multiplexing CPUs. That's where we're getting concurrency so far. Protection is accomplished by restricting access, either by memory mapping or by using kernel mode. And finally, the book talks about processes, and be a little careful, because when the book says process, it's a little bit less clear. So when it's talking about concurrency, that's the thread portion, and when it's talking about address spaces, that's the address space portion. So just be a little careful. All right, go to your new sections on Friday. If you haven't signed up for a section, you better do so quickly.